Dear students, I am Anuradha Rajesh. Today we shall begin session 2 of chapter Light, Reflection and Refraction. Dear students, after today's session you will be able to list and apply the sign conventions used for spherical mirrors and lenses, state mirror formula and apply it to solve relating numericals. Define refraction of light. Relate the phenomenon of refraction to real life situations. Illustrate the path of a ray of light as it travels from one transparent medium to another. State the laws of refraction. In our previous session, we learnt about the image formation using spherical mirrors for objects placed at various positions in front of them. We also learnt about the characteristics of the image formed. In today's session, we will learn to determine the size, nature and distance of images mathematically using the mirror formula. However, prior to learning the mirror formula, we shall learn the sign conventions used for mirrors and lenses. While dealing with the reflection of light by spherical mirrors, we shall follow a set of sign conventions called the new Cartesian sign conventions. In this convention, the pole P of the mirror is taken as the origin. The principal axis of the mirror is taken as the x-axis of the coordinate system. The object is always placed to the left of the mirror. This implies that the light from the object falls on the mirror from the left hand side. All distances parallel to the principal axis are measured from the pole of the mirror. All the distances measured to the right of the origin, that is along the positive x-axis, are taken as positive, while those measured to the left of the origin, that is along the negative x-axis, are taken as negative. Distances measured perpendicular to and above the principal axis along positive y-axis are taken as positive. Distances measured perpendicular to and below the principal axis along negative y-axis are taken as negative. The above sign conventions can be easily related to the coordinate system. If we consider the pole to be the origin and the reflecting side of the mirror to be facing the left side, the coordinate system easily gives us the sign of the respective distances. For instance, the object is always placed on the negative x-axis, that is, on the left side. Therefore, the object distance will always be negative. Similarly, if an image is formed in front of the mirror, the image distance will be taken along the negative x-axis and so will be negative. However, if the image is formed behind the mirror, the image distance will be measured along the positive x-axis and so it will be taken as positive. Before we are introduced to mirror formula, let us learn about certain basic terms and their symbols. In a spherical mirror, the distance of the object from its pole is called the object distance and is denoted by small letter u. The distance of the image from the pole of the mirror is called the image distance and it is denoted by small letter v. The distance of the principal focus from the pole is called the focal length, which is denoted by small letter f. Mirror formula represents a relationship between object distance u, image distance v and focal length f. It is given by 1 by v plus 1 by u is equal to 1 by f. Dear students, always remember to use the new Cartesian sign conventions while substituting the numerical values for u, v and f in the mirror formula. I have some handy tips which will be very useful while solving numericals. Let us have a look at them. The object distance is always negative as the object is always placed in front of the mirror, that is, along positive x-axis. In case of mirrors, the image distance v is negative for a real image while positive for a virtual image. The focal length of a concave mirror is negative since the focus is in front of the mirror, while the focal length of a convex mirror is positive since it lies behind the mirror. Height of the object represented by small letter h is always positive since it is parallel to positive y-axis, while height of the image, that is h dash, is positive for a virtual image and negative for a real image. Magnification produced by a spherical mirror gives the relative extent to which the image of an object is magnified with respect to the object size. It is expressed as the ratio of the height of the image to the height of the object. Mathematically, it is represented by the relation m is equal to height of the image h dash divided by height of the object h. In terms of object distance and image distance, it is given by m is equal to minus v upon u. A positive sign in the magnification would imply a virtual and erect image, while a negative magnification would mean a real and inverted image. If the magnitude of magnification is greater than 1, then the image is enlarged with respect to the object. However, if its magnitude is less than 1, then the image is diminished with respect to the object. Let us solve a couple of numericals in order to understand the concepts better. An object of size 7 cm is placed at 27 cm in front of a concave mirror of focal length 18 cm. At what distance from the mirror should a screen be placed so that a sharp, focused image can be obtained? Find the size and the nature of the image. So, let us first write down the given information from the question with relevant sign conventions. Since object is placed parallel to y-axis, therefore, object size is positive. That is, object size h is equal to 7 cm. Since object is placed in front of the mirror along negative x-axis, therefore, object distance is equal to minus 27 cm. Since the focus of the concave mirror lies in front of it, so it will be negative. Focal length is equal to minus 18 centimeters. The image distance and the size of the image are to be found using mirror formula. 1 by v plus 1 by u is equal to 1 by f. Rearranging the equation, we will have 1 by v is equal to 1 by f minus 1 by u. 1 by v is equal to 1 upon minus 18 minus 1 upon minus 27, which is equal to minus 1 upon 54. V therefore turns out to be minus 54 centimeters. Now, in order to find the size of the image, we shall use the magnification formula m is equal to h dash upon h equal to minus v upon u. Therefore, h dash turns out to be equal to v into h upon u. Substituting the values and after making the calculation, the height of the image turns out to be minus 14 centimeters. The image will be a real, inverted and enlarged one. So now let us move on to another numerical. A convex mirror used for rear view on an automobile has a radius of curvature of 3 meter. If a bus is located at 5 meters from this mirror, find the position, nature and size of the image. Here, a convex mirror is under consideration. Since its center of curvature lies behind the mirror, the sign of radius of curvature will be positive. Therefore, radius of curvature r is equal to plus 3 meters. Object distance is always negative, so we may write object distance u equal to minus 5 meters. We are required to find the image distance and the size of the image. For that, let us first find the focal length of the convex mirror using the formula f equal to r by 2, that is 3 meters divided by 2 equal to 1.5 meters. The focal length therefore turns out to be 1.5 meters. Now, according to mirror formula, 1 by v plus 1 by u is equal to 1 by f. Since we are required to find the image distance, so we would rearrange the formula as 1 by v is equal to 1 by f minus 1 by u. Now, substituting the values of u and v, we get v is equal to 7.5 upon 6.5 equal to 1.15 meters. In order to find the size of the image, we use the magnification formula m is equal to minus v by u equal to minus 1.15 divided by minus 5 equal to 0.23. Hence, the image is virtual, erect and smaller in size by a factor of 0.23. Hope you have understood the questions well. Do practice more numericals. The more you practice, the better you learn. Students, we are familiar with rectilinear propagation of light. That is, light travels along a straight line path in a given medium. But what happens when light enters from one transparent medium to another? Does it still move along a straight line path or does it change its direction? Let us recall some of our day-to-day experiences. You might have observed that the bottom of a tank or a swimming pool containing water appears to be shallower. Let me show you how a lemon looks bigger when I put it inside a glass full of water. It looks bigger indeed. Similarly, if I put this glass slab over printed matter, I will observe that the letters appear to be raised, as you could see. I would like to show it to you once again. The letter I is appearing to be raised when viewed. Now, let us have a look at a pencil which is immersed inside a glass of water. It appears to be broken at the interface of air and water. Let us try to observe what happens when light travels from one medium to another using a simple activity. Here Here we have taken water in this container and added a few drops of milk. Now, when I shine my laser torch into it obliquely, what do you observe? You can see the path of the ray through the water. Now, let me light up an incense stick so that it becomes smoky in the other half of the container, making the path of the ray visible inside air as well. We will be shining a laser torch and try to observe the path of the ray as it passes from one medium to another. What do you observe? Does the light ray bend inwards or outwards when it comes from water to air? So we observe that as light travels obliquely from one medium to another, it changes its direction of propagation. The change in the direction of propagation is due to the change in the speed of light as it travels from one transparent medium to another. For a given pair of media, the medium in which the speed of light is less is referred to as an optically denser medium, while the medium in which the speed of light is more is referred to as an optically rarer medium. So, from our observations, we may conclude that when a light ray passes from a rarer medium to a denser medium, like from air to water or glass, it bends towards the normal. Here, the normal represents the perpendicular to the surface at the point of incidence. When a ray of light enters a rarer medium from a denser medium, it bends away from the normal. So now we know that the apparent displacement of a pencil partly immersed in water is due to the fact that the light reaching you from the portion of the pencil inside water seems to come from a different direction compared to the part above water. This makes the pencil appear to be displaced at the interface. For similar reasons, the letters appear to be raised when seen through a glass slab placed over it. The extent of the effect is different for different pairs of media. For example, the apparent bending of a pencil at the interface of air and water is different from the apparent bending of the pencil at the interface of air and any other liquid like kerosene or glycerine. Hence, when travelling obliquely from one transparent medium to another, the direction of propagation of light changes. That is, the straight line path of the ray in second medium is different from the straight line path in the first medium. It means the ray bends from its original path on entering into another medium. The phenomenon of change in the direction of propagation of light when travelling obliquely from one medium to another is called refraction of light. The two laws of refraction are the incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant for the light of a given color and for a given pair of media. This law is known as Snell's law of refraction. If I is the angle of incidence and R is the angle of refraction, then mathematically it can be written as sin I upon sin R equal to constant. This constant value is called the refractive index of the second medium with respect to the first. We shall be learning about refractive index in further details in our next session. So students, we have learnt quite a lot today. Let us recapitulate our learning. Here we go. New Cartesian sign conventions are followed for spherical mirrors and lenses. Mirror formula gives the relationship between the object distance u, image distance v and focal length f of a spherical mirror. It can be written as 1 by f is equal to 1 by v plus 1 by u. The magnification produced by a spherical mirror is the ratio of the height of the image to the height of the object. Mathematically, it is given by m is equal to height of the image h dash upon height of the object h equal to minus v upon u. The phenomenon of change in the direction of propagation of light when travelling obliquely from one medium to another is called refraction of light. A light ray travelling obliquely from a denser medium to a rarer medium bends away from the normal. A light ray bends towards the normal when it travels obliquely from a rarer to a denser medium. The two laws of refraction are the incident ray, the refracted ray and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant for the light of a given color and for a given pair of media. Here is a task for you all to do. Draw neat ray diagrams to illustrate the passage of a ray of light from air to water and water to air. Solve the numerical problems on mirror formula from your textbook. In our next session, we will discuss the refraction through a rectangular glass slab and spherical lenses. Do keep practicing. Meet you in the next session. Thank you.